Okay, today we're going to look at slope fields and Euler's method. And so first what we're going to learn is what is a general and particular solution of the differential equation. So we need a definition. A differential equation in x and y is an equation that involves three things. It involves the variable x, the variable y, and the variable y prime. Now that, remember, y prime is dy dx. So we'll use any notation, any derivative notation. I'm going to use the y prime notation today, but realize it could be any notation. So we're going to start by doing examples. Now, we're given that the differential equation y double prime minus y equals 0. We want to see if the solution y equals sine of x is a solution to this differential equation. So first thing you got to do is find the second derivative. So we find the first derivative and then the second derivative of y. And then I substitute in my y prime into the differential, my second derivative into the differential equation, and my original function to the differential equation. Now I'm checking to see if I get a true statement, if y double prime minus y is equal to 0 or not. So I get negative 2 sine of x, which is not equal to 0. So that tells me the solution, y equals sine of x, is not a solution to this differential equation. Okay, let's look at this next example. This time y is equal to 4e to the negative x. We're going to see if that is a solution to the same differential equation. So we're going to start by finding our first and second derivative. And we get our second derivative is equal to 4e to the negative x. Then we're going to go back into our differential equation, y double prime minus y, replacing y double prime with 4e to the negative x, minus and replacing y with 4e to the negative x. Doing the math here, I see that that is equal to 0. So 0 equals 0. Therefore, this is a solution to this differential equation. Okay, now I want you to try this problem. Is the equation y equals c to the ex a solution to the differential equation? All right, let's see how you did. So first thing we need to do is find our second derivative. Now remember, c is just a constant, understood to be a number, so the constant comes out. And so our second derivative is also ce to the x. So plugging that into our differential equation, we get that ce to the x minus ce to the x. Well, that is 0, so 0 equals 0. This is also a solution. So notice that one differential equation can have multiple solutions to a problem. Okay, next thing I want to look at is this time I gave you the differential equation x y prime minus 3y equals 0. Now I want you to do sort of like we did in the last problem. I want you to verify that the general solution y equals e to the x cubed is a solution to this. So this time I only have y prime, so I just need to find the first derivative. And then I substitute that into my differential equation. All I need to do is replace the y prime with 3c to the x squared. And I'm going to replace the y with cx cubed. Now, if this gives me also 0, then I know that this is a differential. This is a general solution to this differential equation. We verify it's a solution. And so, yes, this is a solution. Now, what we're going to do is now we're going to find what's called a particular solution. So general solution has that variable c. It has multiple possibilities, could be different constants there. Now, in this case, we're going to find the exact equation whenever we're underneath the conditions. The original equation had an x of negative 3 and a y of c. A y of 2, sorry. And the result that we're going to get is what's called a particular solution to a differential equation. And so this is we must find the value of c to find the particular equation. So I go back to my y equals cx cubed. Now replace in my given information. Replace y with 2 and replace x with negative 3. And then I solve for c. And I get that c is equal to negative 2 over 27. So therefore, the particular solution to this differential equation with the initial conditions of y equals 3 and x equals negative, y equals 2 and x equals negative 3 is y equals, replace the c with negative 2 over 27 x cubed. So equation y equals negative 2 over 27 x cubed is what we call a particular solution to a differential equation. Okay, so now I want you to try one. So given the equation 3x plus, differential equation 3x plus 2y, y prime equals 0, verify that 3x squared plus 2y squared equals c is a general solution. Let's see how you did. So first thing we want to do is we're going to differentiate this general solution. So we find that that's 6x plus 4y times y prime. Now remember, I'm taking this as implicit differentiation. I'm always defining the derivative with respect to the x variable. So make sure you remember to tag on that y prime here. Now I need to solve for y prime because I want to know what my first derivative is. So I'm going to get that term by itself and then isolate the y prime term. And let's simplify this down. I get that y prime is equal to negative 3x over 2y. Now, to verify that this is a solution, I got to go back to my differential equation. And I'm going to substitute in what I found my y prime to equal. So in place of y prime, I'm going to plug in negative 3x divided by 2y. And then I'm going to simplify and see if I get 0 as an answer. Well, let's see what happens. Now notice that the 2y in the numerator and the 2y in the denominator cancels out. So that just leaves me with negative 3x. So 3x minus 3x is 0. So 0 equals 0. It is verified. Now I'm going to take that general solution, 3x squared plus 2y squared equals c, and I'm going to find the particular solution given the initial condition that of the 0.13. So that initial condition this time tells me that my x is 1 and my y is 3. So I'm going to go back to my general solution. Replace the x with 1 and the y with 3 and solve for c. And I get that c is equal to 21. So therefore, my particular solution to this differential equation at this initial condition is 3x squared plus 2y squared equals 21. And that's how you find particular solutions to a initial value problem, differential equation problem.